Hello, welcome back. Today's lesson 3, Limits at Infinity Part 1. In our last video, we went over the epsilon delta definition of the limit. Now, to introduce us to our next concept, I'm going to show you an example of what I'm going to talk about. Here we have the graph for f of x equals 1 over x. We have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. We're going to focus on the horizontal asymptote in this video. What if we want to express the limit of the function as x gets larger and larger, or as it approaches positive infinity? So this can actually help us tell about the asymptotes of f of x, as you can see right here. Maybe you don't have a graphing calculator, or you're not sure if this pattern will continue on forever. So we want to figure out definitively what value will x go to as x approaches positive infinity, or what is our asymptote here. So we'll express this as the limit as x approaches positive infinity of f of x is equal to L. Now we can also put a minus here if you want. This is if you're going to the negative infinity. For f of x is equal to 1 over x, the limit as x approaches positive infinity of 1 over x is equal to 0, as shown by the graph. Look, as x goes larger and larger and larger, right here, f of x gets closer and closer to 0. So we're going to establish some general rules. This is more intuitively right. This is not mathematically right, but it will help us. First, this is true. The limit as x approaches positive infinity of 1 over x is equal to 0. So we can sort of imply that 1 over infinity, positive infinity, or even negative infinity is equal to 0. Here we have the case for negative infinity is equal to 0 because 1 over an infinitely large number, or infinitely small number in the sense that negative infinitely large number is going to be 0. You can test this looking at the graph of 1 over x. Also, if we have positive infinity squared, or to an even power, you're going to get a positive infinity. If you have negative infinity squared, you're going to get positive infinity. Again, we can't actually do this with infinity, but it's going to help us build an intuition around the concept. Now, if we add infinity by any constant, we're going to get infinity, and if we add negative infinity to any constant, we get negative infinity. If we multiply any positive number times positive infinity, we get positive infinity, and we multiply any positive number times negative infinity, we get negative infinity. We really only care about the signs most of the time. So here's an example. Evaluate the limit as x approaches positive infinity of 1 over x squared. Well, this limit is actually just 1 over positive infinity squared, which we know is 1 over positive infinity, which is 0. So that's logically equivalent to saying the limit as x approaches positive infinity of 1 over x squared is 0. Let's evaluate the following limit as well. So this limit, as x approaches plus infinity of 1 over 3x squared minus 5x, we can factor out an x squared to get 3 minus 5 over x, which is equal to 1 over infinity times 3 minus 5 over infinity. This 5 over infinity, remember, we're going to get some infinitely small number, so 0. 3 minus 0 is 3. So we get 1 over infinity times 3, which is just like an infinity, which gets 1 over infinity, which is 0. Now, we haven't definitively proven anything. Again, this is just, concept-based, intuitive, but hopefully it'll help us understand how to evaluate these types of limits. There's actually an easier method, because if we look at the denominator of p of x, only the leading term really matters for the limits. Notice only this 3x squared mattered. This actually just became 0. So we're going to show that by taking the following. This is the limit as x approaches. We put plus or minus infinity because we could do this same process for either one without loss of generality. So we're going to do 1 over, this is just the standard form of a polynomial function. Now we're going to factor out this x to the n. So we're going to have first just our leading coefficient, then we're going to have the next coefficient over x, and the next coefficient over x squared, dot, 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 all the way up to our constant term over x to the n. Here we can use a special rule, which is, we're not going to prove this right now, we might prove that later, but basically the product of any two functions inside a limit is just the product of the limits. So the limit of as x approaches x naught of f(x) times g of x is just the limit as x approaches x naught of f(x) times the limit as x approaches x naught of g of x. So we're going to split this and this. So we're going to end up with this limit of 1 over x to the n times the limit as x approaches plus or minus infinity of 1 over this. Recognizing that all of this actually, in fact, will, since we're going to plus or minus infinity, this is 1 over x, 1 over x to the n, we're just putting with a negative n. So, noticing that all of this will just go to 0, as we have the x in the denominator and x is going to either infinity. So we're going to be left with this. Over here, in that case, since we have the limit of a constant term 1 over a to the n, we can just express that as the constant term itself. So the limit of this times that, we can put this back inside our limit to get that the limit as x approaches plus or minus infinity of 1 over a to the n x to the n, a sub n x to the n. In other words, this holds true. So whenever taking the limit at either plus or minus infinity, the only term that we care about, but the only term that's going to affect it, is the leading term. This is going to be very important, and it's actually very useful. We're going to apply this now. Evaluate the following limit. How do we do this? Remember, all these other terms, they won't matter. In the end, they're not going to matter. So in other words, we can simply express this as the following limit, only writing the leading term. We can take out the constant. That's another rule. We can always take out a constant from the limit, which is 1/4 of the following. And here, since we have an x, or x to the 10, either way, this is going to go to 0. So we get just 1/4 times 0, or 0. Here, notice we don't have a 1 here anymore. We have a rational function. How do we evaluate that? Here's an idea. We can apply the leading term argument to the denominator. The numerator. I misspelled that. Or I put denominator. I meant numerator, okay? So we can actually apply this argument of only caring about the leading term here as well. In other words, we only write the leading terms. We get the limit as x approaches plus infinity of 1 over x cubed, and we get 0. Here, I think I'll just show this. This one's easy. We're just left with the coefficients over each other, and since they're 1, we're just gonna get 1. So now we're going to define the limit at infinity. So we already defined using epsilon delta what the limit at a finite accumulation point is, our x naught. How about at infinity? Well, let's look at positive infinity. The limit as x approaches plus infinity of f of x equals L is defined by, so it's if and only if, for all epsilon greater than 0, there exists delta greater than 0, so we're just copying from any limit, the same format. Here is the only different part. Since we have an x at plus infinity, we have x is greater than delta. So that delta you give, that delta that comes out, the x has to be greater than it, which makes sense since we're going to plus infinity, right? And we literally just again copy this from our original limit. Remember, at a finite accumulation point. And here's the version for minus infinity. Same thing, except here we write x is less than negative delta. We don't write x is less than delta because remember, delta is a positive number and negative delta is a negative number. So we have to say x is less than that negative number. Otherwise, if we just write delta, x is less than a positive number, which is obviously true. And we just copy this from our original limit. Before we actually start solving anything, we have to recall some properties. If x and k are both greater than 0, 1 over x being greater than k implies x is less than 1 over k. If you want, here's how to prove that. And same thing, if it's less than k, we just remember, take the reciprocal, flip the sign, and take the reciprocal. Now, using our definition of limit, let's prove the following. The limit as x approaches positive infinity of 1 over x squared equals 0. Now let's write our definition for all epsilon greater than 0, there exists delta greater than 0 such that x being greater than delta, remember this is at positive infinity, so we write x greater than delta, implies the fx minus our limit is less than epsilon. Right here, these two express the same exact thing. Proof. Let us fix epsilon greater than 0. Again, same exact thing. This time, I'll show you where it gets a bit different. The entire process is the same. The only thing that's different is our end point. So remember, we can apply the property up here that we defined, or that we discovered. We can actually use the property of absolute value to just put the absolute value to each term, and we could take the reciprocal, flip the sign, take the reciprocal. We can take the squared out of the absolute value, and this is implied by the absolute value of x is greater than the square root of 1 over epsilon, which is implied by, we're going to use remember, when we have a greater, we can use what's known as the disjunctive inequality. If you don't recall, absolute value of x being greater than k implies that x is less than minus k, or x is greater than k. And this is just implied by, like I said, the disjunctive inequality. If we had x, the absolute value of x is less than, we can use a triangle inequality, so that's some building problem solving. But since it's greater than, we have the disjunctive inequality. And since we have this disjunct, remember, this can be implied by just any of them being true, so we can just assume this one is true here, since that's going to imply this. And we have x is greater than something. And remember, that's where we want to finish, delta, so we can just define this to be our delta, and we're done. Now we're going to prove the following limit. Now we already saw graphically why this is true, but let's prove it here. So for all epsilon greater than 0, there exists a delta greater than 0 such that, remember, we're going to write, since it's at negative infinity, x is less than minus delta implies f of x minus L, the absolute value of f of x minus L, is less than epsilon. Proof. Fix epsilon greater than 0. Here we're going to, again, copy this here. This is implied by, we're going to just take the reciprocal, flip the sign, reciprocal. Here we have, we're going to use the disjunctive inequality to split. Here, when we're doing it, we want to use the disjunctive inequality because any of these being true makes the whole thing true. If we have a less than, then we're not going to use the conjunctive inequality. That's going to make our life harder because we have an and then. And we're going to have to prove both, and that's not going to be efficient for us. So this is implied by this. And basically, what I'm going to say is that we're going to look at what we want to get. We want to get x is less than minus delta. Here we have an x is less than minus something, or x is less than. So we're going to take this one and try. So x is less than minus 1 over epsilon. And we could just define this to be not our delta, not our delta. We have to make sure this is our minus delta, because remember, if we just define this to be our delta, epsilon's a positive number, this is going to be negative, and we're going to get a contradiction. So we have to put minus delta, since also x is less than minus delta, not x is less than minus delta, not that x is less than delta. Let's prove the following limit. Now we know by the leading term argument, here this is going to be going to 0. If and only if we'll write out our definition. fix epsilon greater than 0. Now, f of x minus the limit is 0, so we'll ignore that less than epsilon is implied by. We're going to take the reciprocal, flip the sign, and take the reciprocal. And since we have greater than here, we're going to use our disjunctive inequality. Here, you may be wondering how we're going to do this. I'm going to have to show you something, and this is very important. So, starting off, first, we're just going to go here, take, which one? Well, x is going to plus infinity, so let's see which one of these is true. This is going to be infinity plus infinity minus whatever, but remember we only care about our leading term, so this is just going to be positive infinity is less than minus 1 over epsilon. This is obviously not true. And here we just have infinity is greater than 1 over epsilon. Yeah, this is true, so we're going to take this one. So this is greater than 1 over epsilon. This is implied by whenever we have, so let's remember, we're working backwards, so this may get confusing. But does this imply that? Well, if this is greater than 1 over epsilon, wouldn't you say that 3x to the 5th minus 4x to the 3rd, 3x to the 5th minus 4x to the 3rd plus 2 is actually going to be to the right-hand side, and we know this is 1 over epsilon. So, in that case, we can notice that obviously this has to be to the right of 1 over epsilon. In other words, this is true. So whenever we have a greater than, we can always add a number, right? It'll still be true because now the number is even going to be even bigger now. So here, this is true. We can just eliminate this, very easy. And how do we do this? This is where we really have to think now. Because notice before we learned how we could do 3x to the 5th greater than 1 over epsilon, 2 epsilon, and 4x cubed minus is greater than 1 over 2 epsilon, and we can add them and we can get 1 over epsilon. This doesn't work because we actually have a minus here. Instead, what we're going to do is that we're going to write 3x to the 5th greater than 2 over epsilon and 4x to the 3rd. That way we have a positive number now is greater than 1 over epsilon. But why? Well, if we subtract the 2, what are we going to get? 2 minus 1 is 1 over epsilon greater than 3x to the 5th minus 4x cubed. And we have exactly what we want. So let's try that. So both of these have to be true, 2 over epsilon, 1 over epsilon. We just have to find that this minus that is 1 over epsilon. We could choose anything, 3 epsilon and then 2, 5, 4. We're just going to choose the easiest example, 2 minus 1. So we're going to isolate our x here. X is greater than this, x is greater than this, if this and this is true, which is implied by, remember, we talked about how the minimum and maximum functions kind of work. So, in other words, if this is true, if x is greater than, this is true if x is greater than the maximum between these two, because if it's greater than the maximum between these two, then it's greater than the biggest one, so of course it has to be greater than the smallest one. And since we have x is greater than, which remember that's our goal, we can just write it, set this to be our delta, choose it to be our delta, and we're done with the proof. Here's our final practice. We're going to have 2 evaluations and 1 proof, so you can try this out for yourself. You can pause here now. Okay, now let's start off here. Evaluate the limit. Now notice we focus only on the leading term, so the limit of x approaches negative infinity of the leading, minus, we only have the leading term here, we can take out a minus 1/4, but the point is that this is going to be 0. In general, actually, when the degree of the bottom is greater than the degree of the top, it's always going to be 0. Maybe if you took pre-calculus, you'll remember the horizontal asymptote is at 0 if the degree of the denominator is bigger than the degree of the numerator. This is why. This is actually the proof. A lot of things you learn can be proved with calculus, even though you learn it really early in like algebra. So let's evaluate the second limit. Again, first, which degree is higher? This is 3, this is 4. So we're going to guess 0, but let's just do the leading term anyways. Take only the leading terms. This is the limit as x approaches plus infinity of 2 over x. And yeah, as we expected, it is 0. Here's where we have a bit of a harder one. We have to actually prove the limit. Remember, some problems may actually ask us to both evaluate and prove, in which case we'll have to do kind of this off to the side first, maybe, to find out that it is 0. There's no need to take like really big numbers like this, because this is going to be wasting a lot of time. It's just more useful to do like algebra, and it's actually a lot more solid, because we'll learn later on. We can prove these properties actually later on. So prove the limit as x approaches negative infinity of this function is equal to 0. Now, if they asked us to evaluate it and prove it, and we didn't have this, we could still figure it out as 0, but we already have it, so we're going to write out our definition, plugging in our f of x here, minus our limit, and all the absolute value of this is less than epsilon. So, for our proof, we're going to fix epsilon greater than 0. So our f of x minus L, the absolute value, is less than epsilon, which is implied by reciprocal, flip the sign, reciprocal. And we're going to use, since the absolute value is greater than, we're going to use disjunctive. Remember, if we had less than, we would use triangle inequality. The reason why triangle inequality doesn't work is because we wouldn't actually get anywhere. Triangle inequality would only work if we know that this is less than, because then we have the sum as well of the square roots, and this is less than epsilon. But remember, since this is not true, we can't actually infer anything. So we're going to use our disjunctive inequality here. And which one are we going to pick? Well, look, we're going to minus infinity. So which one of these statements is true or looks true? So this is x to the third, so this is just going to be a minus infinity. So this minus infinity is less than any number, so we're probably going to pick this. But just to check, minus infinity here and greater than 1 over epsilon, this is not true. So we're going to pick our first one, right? We only want to pick true statements, because we know if we pick a false statement here and work off of that, at the end, we're not going to get our answer. So this is true. We're going to assume this, and that implies the disjunct. And now we're just going to move minus 4 here. If we had greater than, again, remember we could just eliminate the 4, but we're going to have to subtract by 4 since we have less than. Whenever we can eliminate, we should. It's going to make our lives easier. And there's another reason why, but I'm not going to show that. So here we're just going to isolate x using algebra. So x is less than this expression, and we're going to choose that to be our minus delta. Remember, when we have a limit as minus infinity, we have to choose this to be our minus delta. And we're done, because x is less than minus delta implies that the absolute value of f(x) minus the limit is less than epsilon. So that's it for limit as x approaches plus or minus infinity. Hopefully this helped a lot in both evaluating and proving these types of limits. In our next video, we're going to be going over the vertical asymptote, or as the limit goes to positive infinity or negative infinity, and as x just goes to a finite point. And then at the end, we might be able to combine the two and say, as x approaches infinity, the limit also goes to infinity. And then we'll be, I think, completely done with the epsilon delta limit definition and it's in its entirety. So hopefully this helped a lot, and good luck.